So in this video we're gonna talk about compact set, and we're gonna spend some time on it for this module. Before that, I like to add few items, few exercises that I ask you to go over. So I won't grade them, I just ask you to do them. Those exercises are really easy. Let's begin with the first one. It says one thing. So you take a metric space E, we equipare with a metric D, and you take two sets A and O. Assume that O is open, and I know one thing about O versus A is that those two sets do not intersect. Well, what I'm asking you to show is that the open set O does not even intersect the closure of A. So this is something which is that's a result which is an exercise which is very classical, and this exercise is actually of need for showing the next one. It's also a very classical statement. Assume that P is included in E, the same space, and P is connected. Then I'm telling you that the closure of P, that is, remember what the closure of a set is the smallest closed set that contains the set. Reminder that the closure of a set B, it is the smallest closed set containing B, or is the set of points this is a set of points in E such that for any ball centered at this point and of radius epsilon, you do intersect B. So in other words, these are the accumulation points of B added to the set B, if you prefer. Alright, so in other words, by considering the closure of the set, you do not destroy the connectedness of the set. Pay attention, if I do the reverse operation, it's not exactly the reverse, but if I take the interior of a set, this could be, this may not be connected. You see, for example, if I take a double 8 figures with, let's say, those two discs in this set, the interior of this set, you will have, for considering the interior of this set, you will have to remove the point, and then those two sets will be disconnected, because I can find two open sets that covers those two balls, in other words, and do not intersect in the set per se. Alright. Finally, there's also another thing which is also quite easy, and it's just a direct consequence of Morgan laws. Remember how we define a connected set. A connected set is a set for which every covering of open set O1, O2 that satisfy O1 intersected with O2 is empty in P. So that is O1 intersected with O2 intersected with P is the empty set. And O1 union O2 covers completely P. If we can find this guy, the conclusion is that if P is connected, one of those sets, the trace of those sets in P has to be empty, either one or the other. Well, here it says exactly the same. I reformulate the same question, but you can replace the word open by the word closed. Well, it's easy. Just consider the same wording by means of open set, and consider the complementary of O1 and the complementary of O2. O1 and O2 will be two closed set, and you will see that there will be some nice algebra going on with this story. And you can conclude actually, you can replace the word open by the word closed by when you talk about connected set. Alright, so this ends pretty much what I wanted to tell about connected set. And let's say, independently from a connected set, this is also a quite classical exercise, which I haven't seen, I think, in the book as far as I remember, but it's extremely elementary. You should be able to do this exercise. Alright. So now let's talk about another topic, which is the notion of compact set. So exactly in the same way as I did for connected set, I will first define what is a compact space. All right. And then we will see what are compact subset and subspaces, but more precisely subsets will be more handy. So first of all, let E D be a metric space. And I'm going to let's say investigate what does it mean that E is compact. Definition. E is said to be compact if for all family, so for all family of open sets let's call it UI, where I belongs to a set of index I. Again, I doesn't need to be finite. You can think that I has a huge cardinality, and you will see in many cases that we will consider I is absolutely not finite. If for every if for all family of open sets that satisfy the union of the I of UI equal E. So in other words, that's what we call it a covering. We cover the full space, right, with open sets. Then there exists actually indeed in the set of index n I, there exists a set, let's call it A, included in I, of finite cardinality this time. Or in other words, we could say, that means exactly the same thing. There exist I1, I2, let's say P belonging to I, such that, let's write ST, it's better, the union from J equal 1 to P of UIJ, that is only the union of those open set already covered. So you have to read the definition very, very carefully. It says that give me a covering of open sets, and this covering has absolutely no reason to be finite. Well, it tells me that the set is compact if and only from that covering I can deduce a finite subcovering. Right, that's precisely what it says. Right? So it's actually the definition is quite weird. The first time you see this definition is quite scary. And but the good news is that pretty much for what we're going to do in topology, in functional topology, this is pretty much the definition that we will need. You guys know that compact sets in the real line are closed and bounded. This is something that we will let's say recover. The contrary is true as long as we consider the Euclidean norm on Rn, on any vector space, let's say isomorphic to R, and of finite dimension. It is no longer true if the dimension of the space is infinite. There is a lot of counterexamples. We'll go over quickly out of this theorem that a compact set in a finite dimension and for the Euclidean metric is closed and bounded and vice versa. But actually we will do more. There is here a definition that we could completely reformulate. Instead of taking open set, we can take closed set. So how do we formulate this? By simply taking the complementary of this claim. Let's take the complementary of this. And take, of course, therefore, the complementary of this. What does it tell me? It tells me, so the complementary of a union is an intersection of complementary. So let me do it like this. The complementary of E is nothing else than the empty set, obviously. And complementary of OI are, of UI, sorry, are closed sets. So I'm going to call it Fi. So let's say the Fi, at each UI I define an Fi, which is just the complementary, it's complementary. And it tells me that, so it's not a covering anymore, no, it's an intersection of closed set which are empty in here, of course. Then it tells me that there is a finite number of, a finite subset of the index I, or I1, I2, In in R, such that we got exactly the same thing, but the intersection from I equal 1, from j equal 1 to b of Fij equal, it's already empty. So in other words, take a family of closed set that for which the intersection of all those sets is empty in this compact set. It tells you that, well, you should be able to find only a finite number of those finite sets for which the intersection is empty. So this is yet another way to formulate, to give a definition which is completely equivalent for a set E to be, for a space to be compact. Now, I just have formulated the notion of compact spaces. I also want to formulate the notion of compact sets. What about if E has no reason to be compact, say, but I take a set K included in E and I want to say that K is compact. What does it mean? Well, there is the lazy way to say is to say this. And then we're going to translate what it really means. The lazy way is to say K included in E is compact if and only if K as a subspace, that is K occupied with the same metric D, is compact. Alright, so well, this is not something extremely exciting, but what does it mean that K as a subspace is compact? That means that we need to consider open set for K. Alright, so let U, I'm going to put F K I, so let's say this like that. A collection or a family, a collection of open sets for K. Which means what? That means that all those UKI are actually the trace of open set in E intersected with K. So these are some OI intersected with K, where OI is an open in E. And it's easier ways to consider open set for the full set than for a restricted set. I mean, because you will see later on, we'll consider sequences of compact set. I mean, we don't want to change topology at each time, so we want to stick to one topology, and that's it. So this is precisely what it takes. How do we formulate again that K is compact? I will say that the union of UKI from I belonging to I equal K. What does it mean this? Now by means of this let's say traduction, in other words, the union from I belonging to set of index I of OI intersected with K equal K. Well, by distributivity of the intersection with respect to the union, you could say that this is nothing else than this. Alright, so how can we translate this in other words? I want to get rid of this intersection here. Well, you can do it by saying that this set here intersected with K is equal to K, so that means that this set is bigger than K by means of inclusion. So K is covered. So yeah, you can really now think about a notion of covering. So it could be that the union of those OI go even beyond K. That's fine. And now I will say that K is compact. If if I can find a finite number of those UKI in such a way that it covers. So I should have said let. So K is compact. Let me say this time. K is a compact set. K is included in E if for all covering K is included in the union of I belonging to I of the OI, well then there exists I1, IP, finite number of those guys, such that K was equal, remember, to the union from J equal 1 to P of U K Ij. But then I can replace those UKIJ by the union from J equal 1 to P of those OIJ intersected with K. So K equal this yet again. Well, you see, you just say this quantity is included in the union from J equal 1 to P of OIJ. So yet again here, here this is very simple to understand the notion of compact set and not necessarily compact space, where the set K is strictly included in it could be E itself, it doesn't matter. But this generalizes the notion of compact space even. Right. So if you cover your set by any family of any union of open set, well, this union can be revisited in such a way that you throw away all of them except a finite number, and you still cover the space. All right. So that's now for the definition of a compact set. So now there's a lot of properties about compact set, and it is quite remarkable that we can do a lot of things. We can do absolutely marvelous things in topology, thanks to the notion of compact set. We do not we have absolutely no idea, because it looks like some wording from set theory. But we will be able to show, for example, thanks to the notion of compact set, that every norm in Euclidean space of finite dimension are equivalent. We will be able to show, thanks to the notion of compact set underneath, we will be able to show the mean value theorem, which has absolutely nothing a priori with the notion of topology, and it's more something which deals with a differentiability. Well, actually, the hard part of this thing comes from the notion of compactness. All right, so first of all, let's let's talk about basic properties. So from now on, I'm not going to talk about compact spaces, but compact set. If we want to talk about compact space, we can still take the definition I've given for compact set. It's perfectly all right. You can always say that E is included in a union of open sets, which are all included in E. That's fine. That means that E is equal to this union. That's fine. All right. So the first thing is, the first proposition is, and it's easy really to show. K is included in E. K is compact. Then K is closed. Well, this is a very classical result, and I'm going to show this in a minute. No, I don't want to show it closed yet. I want to show, first of all, K is bounded. First of all. Bounded. To begin with. We will show that K is closed after. So I will use this shortcut for bounded. I would avoid spending too much time on it. Alright, so this is actually a very classical thing. How do we show this? Well, take proof. Take X in K. So okay, there's one thing I want to say. If K is empty, well, if K is empty, well, you can make a lot of you can cover the empty set by many set you want. You can take any covering, and then of course you can subtract any subcovering. So let's don't discuss about trivial case. If K is empty, yeah, K is empty. K is clearly compact. I'm not going to talk about that. So let's assume that we have at least one element in the compact set K. Then consider the following family of open set: the ball centered at X and of radius n, the integer n. So you see, these are balls bigger and bigger and bigger. I claim that the union of all those balls covers K. Yeah, why? Because, I mean, if I take the union of all those balls, I can cover actually all the space, actually. I can do even better. Yeah. Why is that so? Take any point in E. Let's say call it Y. It has a distance with X. It goes a distance capital D. Take N sufficiently large, it says the way that N is bigger than D. B and X contains Y, so this means that this guy contains every point in E. So of course, we have something like this. Alright, but K is compact, so this means that there exists N1, N2, Np, a finite number of those balls, such that the union from j equal 1 to p of b and j of x contains K. But no mistake, those balls are all with the same center. So actually this guy is nothing else than B of M of X where M is nothing else than the max of those NP. And have the fact that the ball centered at X and of radius quite large, and anyway, maybe very super large, that doesn't matter, contains the set K. Well, that's precisely the definition of being bounded. You are included in a ball centered at a point. That's it. So that's the proof, so it's very classical. Now let's prove another proposition. So I was making a lapsus before. Let's say, I want to say that K is closed. So here, okay, so before I'm saying anything, I'm going to erase that bit. So here, observe one thing. This claim would not make any sense if I will say, let's take a space E and assume that the full space E is compact. of course I'm going to get the fact that E is closed because it's already included in the topology. So you see here there's a bit a fishy wording. So that's also one reason why people like me and others do not like to talk about induced topology too much, and we prefer to adapt definition of connectedness and compactness not for space themselves but for sets. So that's why don't be surprised that in the book it speaks about connected set again, but not connected space, but not connected set. Again, the book introduces the notion of compact space, but doesn't speak much about a compact set. So you have to pay attention about that. But it's not so hard, especially for compact. The distinction is very easy. All right. So we have to show that a case closed. We have to show that what is it? That K is to show is open. So that means what? That means that let Y not in K. Or that means the same thing, Y belonging to K complementary. There exists a delta positive such that the ball centered at y end of radius delta does not intersect, is still included, sorry, it's still included in the complementary of K, or equivalently, it says that the ball centered at delta, centered at y and of radius delta, does not intersect K complementary. Does not intersect K. That means that those two words means the same thing. So a picture maybe is needed. This is your compact set. I want to show that it's closed. I want to show that the complementary is open. Let's take a point outside. I want to find a delta in such a way that I can do this. I can do this separation in other words. How can I do this? Well, actually, the magic thing here on the proof, I'm going to be able to do a little bit more than showing that it's closed. I will be able to do the following thing. I will be able to show that there exists an open set U containing K. K here. This is an open set containing K. And I will be able to show that there exists a delta positive, such that the ball centered at delta and of centered at y and of radius delta does not intersect not K only, but U also. How am I going to do this? And actually, this proof can be extended not only for metric space, but for Hausdorff sets. So I need to, for proving this thing, I need to have a lemma, which is, I'm going to leave it as an exercise because it's very easy. ED is a metric space, is Hausdorff. Okay, so the spelling for Hausdorff, normally we have a S set, so some sort of beta in between, so I just put double S in such a way that nobody's surprised, but it's a German word. What does it mean that a space is of Hausdorff type? Meaning that if you take two distinguished points, X and Y belong to E, there exists an open set containing X that doesn't contain Y, an open set that contains Y and that doesn't contain X, and for which those two sets are empty intersection. This is what it says. Right. In the case of the metric space, it is always guaranteed. You take X belong to E, Y belonging to E, and take, let's say, I'm going to call it rho, equal the distance of X and Y, let's say divided by 3. Why not? You can divide by 10 if you want. That's fine. I'm claiming that with this choice of rho, if you take the ball centered at X and of radius rho, this does not include y. If you take the ball centered at y and of radius rho, this does not include x, and not only this, but but the intersection of those both balls is empty. Well, why is that so? Because if we had a point in the intersection here, suppose that we have a point which is also in this ball. That means that the distance between x and this point is rho, less than rho, and the distance between this point and y is also less than rho. So that means that the distance between x and y is less than rho plus rho. But rho plus rho make 2/3 of the distance of xy. No, the distance of xy is already given. So you could not have a distance of xy less than 2/3 of the distance of xy. So metric space are always satisfying this property, and this is what we need here. Well, actually, I've just said that, but we might not. I'm just going to make the proof without this assumption indeed. All right, so how am I going to show this? So let me write down what we will show. We will show that there exists an open set. So an open set, I would like to say that there exists an open set U containing K, a delta positive such that the ball centered at y and of radius delta intersected with u is empty. That's what I'm going to show. Proof. I like to keep this picture, but I'm going to remodify everything. So the assumption we have, proof. The assumption we have is that y doesn't belong to k. So for all x belong to k, I claim, so x belongs here, I claim the distance between x and y is positive. Well, let's call this distance d of x. I mean, since y is fixed, I don't need to specify the dependence in y. All right? And let's take rho equal dx divided by 3, exactly the same way I did before. I claim that the ball centered at x and of radius rho intersected with the ball centered at y and of radius rho do not intersect. Well, for the same reason as I said before. You see, you have x is here, y is here. The distance here is dx by definition, and you take, a ball of radius 1/3 of this distance. So if a point here z happens to be also in this ball by accident, that will mean that the distance between x and z plus the distance between z and y, remember, thanks to the triangular inequality, is always bigger than the distance between x and y. But this guy will be less or equal than, if it belongs to this ball, it will be dx divided by 3, plus, since it also belongs to this ball, dx divided by 3. And this is equal to dx. So you have dx, which is a positive number, of course, which is less than 2/3 of dx. That's impossible, because 2/3 is less than 1. Alright, so this is something which I have a tendency to repeat myself. Again, here we do not necessarily need the fact that we have a metric, but the fact that the topology is so the set, the base of the topology, the family of open set that generate the topology, not only the ball, but it could be anything you want, separates points in the way of Hausdorff I have defined before. All right, so that's great, and I'm going to do that for any x in K. So I'm going to erase this. For all x, I take this ball centered at x and I've reduced, so I should say rho x because rho depends on x. Alright, so now I can say that I can take the union of all those balls centered at x and I've reduced rho x. And you know what? Since x itself is in the center of all those balls, so it's a huge union, you know, especially even for this picture. If I want to take all the points on the ball, I would have a hard time to count them, in other words. No, it's really an uncountable union. But nevertheless, it definitively covers K, because the center of each of those balls is already in K, and I take the union of all x in K. So clearly, this is clear, this is true. But now this is where the compactness of K is important. It tells me, well, you have taken a huge, let's say, an infinite number of balls, yes, but you could have taken from this set only a finite number. Oh, that means that there is only a finite number of points in X that satisfy this. Alright, so this means that there exists X1, XP, such that, let me erase this bit here and I will redraw it after, such that the union from J1 to P of the ball centered at Xj and of reduced rho Xj, so I'm sorry if this is a triple index, already covered K. Well, you know what? This guy here, this is a finite union of open ball. Open balls are open in the sense of the topology. A finite union of open ball is open. And I'm going to call this set U. Alright, now let me redraw the picture yet again. And this guy, so this is K, this is U, alright, which covers completely K with a finite number of balls, and let's say let me Y here. Now, what do I have? I need to erase something. I don't need this thing here anymore, and I don't need this anymore. So maybe I should say this like that. Take U equal. Now, what do I do with on the other side with Y? You see, for each of those X, I could associate a ball centered at Y and I've reduced rho X. Now what I'm going to do, I'm going to take delta is equal to be the minimum of all those rho x1, rho x, rho x1, rho x2, and so forth and so on. So rho x1, rho x2, up to rho xp. And what do I have? I claim that the ball centered at delta and centered at y is obviously included in the ball centered at y and of reduce rho xj for any j I choose. Yes, why is that so? Because I took the precaution to take the smallest one. So this ball is included in this ball. If a ball is of small radius, it's of course included in the former. All right. But what did I know? I already know that, so I need to erase a part of it. I know that B rho xj y doesn't intersect the ball centered at x and are the same guy. I know this. This is by construction, by definition. If it is going to be true, if I take this set smaller, this is going to be also true. And this is true for any j. So if this is true for any j, let me erase this now. This is going to be true also for the union. So that means that B delta of y intersected with the union of Bx rho xj from j equal 1 to p is also empty. Otherwise, if this intersection were not empty, this means that there will be a point here and a point in one of these balls. No, it says it's impossible because it's true for any j. But this is nothing else than u. Again. And this ends the proof of my proposition. I find a delta positive, which is the minimum number of all those the radius of those balls, and I find I like to call it a neighborhood. We'll talk about neighborhood later. I try to avoid this wording now because it could be confusing. I find an open set that covers completely K, and those two guys do not intersect. So I've proven a bit more actually than the complementary of K is open, that is K is closed. I've shown that we can separate point and compact. Actually, we can do also a little bit more, and this I leave this as an exercise. And the technique for showing this exercise is using the same thing as this exercise. Let K1 and K2 be two compact sets in E, of course, always. Assume that K1 intersected with K2 is empty. Is empty. My apologies. Then the conclusion is that there exists open set U1, U2, such that U1 contains a K1, U2 contains K2, and exactly what you feel, U1 intersected with U2 is empty. So the picture is like this. You have a compact set here and another compact set that do not intersect. But you can really do like we are thinking of being able to do in the two-dimensional space. We can find open set U1 and U2, including both guys respectively, in such a way that they still do not intersect. So I leave this exercise for you guys. It's a very classical exercise, let's say, that we sometimes put in the qualifying exam. So I would not underestimate the difficult, let's say, I would not neglect this exercise. It's not hard. The idea is pretty much the same thing. You take K1 here, you take a point, you take K2, and you take a point Y in K2. You know from what I said before that you can isolate a point and a compact. Well, do it now. Take a set which I'm going to call it UI because it depends on UI. You take a ball here and you do this, a ball centered at Y and of reduce delta, the thing I did before. And you do it again for all Y in K2, and you're going to cover K2 with a finite number, eventually with a finite number of those balls, and you're going to take the intersection of all those open sets. But the intersection, a finite intersection of those open sets will still be open and still cover K1, and then you will get a covering for K2. So I let you think of this exercise. It's for good practice. Alright, so I've shown that a compact set is closed, is bounded, so there's all the thing that we need to know. Something quite classical as well. Before doing what I like to call the hard stuff. Proposition. So I could actually formulate this proposition by means of compact space, but again I prefer it to do by compact set. Assume K, included in E always, K is compact. So you take a compact set of E, and F closed set and F included in K. The conclusion is what you will get easy if you assume that compact means closed and bounded, which is, remember, not necessarily true if the dimension of the space of the vector space is infinite, right? Then if you assume that this is true, of course this proposition is completely evident. F is closed, therefore F is compact. Yeah, well, quickly, if you say that closed and bounded means compact, and they means really the same thing, which again, as I say, it's not necessarily true if you consider, for example, vector space in infinite dimension. But let's say in Rn, that will be true, because F is already closed, F is included in a set which is compact, and the compact is bounded, so F is also bounded. So F is closed, bounded, compact. Down. Now here I want to do a proof which also includes the case where closed and bounded does not necessarily mean compact. How are we going to do? Well, let's proceed by a covering. Let's OI, where I belonging to I, be a covering of F. So I'm not going to repeat all the same word all over. Sometime when I want to speak about a covering, I will say let a union of OI, when I belonging to I, contains therefore F be a covering. So that is, maybe I would like to write it like this. Alright, what do we want to show? Remember, this is always good to say. We want to show that there exists I1, IP, such that the union from J equal 1 to P of OIJ still contains F. So I can deduce from this covering a finite covering. So here I don't know how to do that. So what am I going to do? I'm going to deduce from this covering a covering not of F but of K. Remember, K is compact. So what I'm going to do is this. Let's F complementary union, this union, I belonging to I of OI. So this definitively I claim that this covers K. Why is that so? First of all, F was assumed to be closed, so F complementary is open. This is a collection, a union of open set, so this is open, everybody is open. So certainly this is a covering, assuming that this is true. I mean, do I really mean that every point in K is included in this? Well, there is two possibilities. A point in K, so remember we have F included in K. There is two possibilities. Either a point is in F or is not in F. Or if it's not in F, it's here. And if it is in F, is therefore here, so is therefore here. So yes, we got a covering of K. But now K is compact. So it tells me that there exists, so since K is compact, there exists a finite covering of these things. So there exists I1, IP, deduced of course from this set, because I mean I could probably remove F complementary, maybe it will be enough, but you know what, I need certainly to remove let's say most of those open set and keep at most a finite number. These are the ones. So I1 IP such that, well, it doesn't hurt, I can say still F complementary union the union from J equal 1 to P of Oj still cover K. But then I'm done. Because it covers K, but it also covers F, of course. So it's definitively this guy cover F. Yes. Am I finished? Yes, I'm finished, because here I don't need this guy to cover F. I mean, F is not going to be, I mean, the intersection between F complementary of F is empty by definition. So if F is covered, is already covered by this guy. And this exactly ends the proof of what I wanted to show. So therefore, if a set is closed in a compact set, it inherits also the fact that this set is also compact. All right, well, that's good. So, as I said, there is an ultimate goal in this part of the module, is actually to show a bridge between two notions. So, let's say, I have an ultimate goal that includes the fact, includes to show the fact that in Rn, we equipied with the Euclidean metric, every closed and bounded set is compact. So in other words, the reciprocity of what I said earlier. Actually, as I said, I will do more than this. I need to introduce for that another notion of compactness, which is that of sequentially compact. Definition. So again, K is included in E, where E is a metric space. I could always talk about, let's say, directly by means of compact space, but I prefer to talk in this setting. We said that K is sequentially compact if, and only if, so it's a definition, for all sequence xn, where xn belongs to K for any n, there exists a convergent subsequence so it converges to something, let's call it L, where L still belongs to K. So you see, you could have formulated this definition by means of sequentially compact space. So for any sequence in the space, there exists a convergent subsequence. And of course, but I want to make sure that we have a stability of the limit, so the limit does not go outside the set. So that's why I prefer to speak about sequentially a set which is sequentially compact instead of a space which is sequentially compact. But if you understand this notion, you understand the notion of sequentially compact by means of space. That's the same thing. All right, so this is yet another definition, and this definition looks quite different than the one we have seen earlier. Right? It's really not the same, and first of all, it's clear from the definition I gave about convergent sequence that we need to have a metric to define the notion of sequentially compact. Well, actually, we don't. We can define convergence of sequence without matrix. It doesn't really matter, but it's not really subject of what I want. Actually, this is what the ultimate goal would be to show that in the frame of matrix space, even of infinite dimension, compact in the way I defined earlier with the covering, and sequentially compact are the same, Unfortunately, sequentially compact do not necessarily mean compact if the space does not have any metric and the topology is a bit more weird, but this is not something that we're going to see. However, there's something which is always clear, is compact always implies sequentially compact. So this is actually the next proposition, which I'm going to state now. So maybe before I speak about this, let me quickly show you the strategy that we're going to follow. So we have two notions, compact and sequentially compact. And I want to show that in the frame of metric space, they really have the same. So what I'm going to show is that this is always true. What I will show, I need to show that the other side, but there's not going to be that straight. It's going to be much harder. What I'm going to show is that a set which is sequentially compact is automatically totally bounded. We'll see what the notion of totally bounded means. Is a notion which is quite important and is sometimes quite redundant in the qualifying exam. So we'll speak about that. Thanks to the fact that a set will be totally bounded, we will be able to show, thanks to the sequentially compact, so we need these things plus this thing, that, so I'm going to say it very schematically speaking, that for any covering, we can associate a Lebesgue number. And we will see what this Lebesgue number means appropriately in terms. And finally, thanks to this Lebesgue number and the fact that it's totally bounded, so together with these things, we will be able to show that something which is sequentially compact, so sorry, it doesn't go like this, but it follows these things. It's totally bounded plus this means this. So you see, so the strategy is this one. If you know that you are sequentially compact, you know you are totally bounded, and because of the fact that you are totally bounded, you have also and you are sequentially compact. I need those two things. Huh? So you will get the Lebesgue number, and if you have this Lebesgue number, we will be able to show the compactness of the set. It's a little bit more subtle because you really need to have both things. Right. So there is a reciprocity here, which is not completely the same. A set is totally bounded. That will imply the set is not necessarily sequentially compact, but it tells you that for any sequence in the set, I can deduce a Cauchy subsequence. So it's a little bit more subtle. And this is actually a part of those exercises which are at the end of the chapter. And this is pretty much in this spirit that I would like to end this complete model. So first of all, I'm going to show the following proposition: compact implies sequentially compact, and that's where I'm going to stop this. I'm going to stop this section, and then in the next session I will finish the module. All right. So proposition. Compact implies sequentially compact. Compact. All right, so sequentially compact. Let's discuss the proof of this. So let K be compact. So we want to show that for any sequence in K, we can deduce a converging a subsequence. All right. So let xn be a sequence in what? In K. All right. So there is already one situation in which I would like to avoid. We're gonna assume, for simplicity, not for simplicity, but to avoid a trivial case, that the range of xn to be infinite. Yes, because if the range, what do I mean by the range of x? Well, this is very simple. This is simply the set, all the set of points that are reached by the sequence. If this set is finite, that is consisting of only a finite number of points, say like this, well, that means that what? That means that since I have infinite number of index, but I still have a finite number of points, that means that there exists at least one of those guys, let's say this one, for which the sequence, let's say it's this point infinitely many times. Well, I'm not necessarily mean that the sequence is periodic, but it's. But that means that if I take all the integer n such that xn is equal to this point p0, say, let's call this set n0. Well, I can define clearly a convergent subsequence. Take x of phi of not phi of n, xn, where n belongs to n0. Or in other words, if you prefer, since n0 is an infinite set, there exists an injection or an increasing map from n to n0, which is just saying what is the first number of n0, what is the second number of n0, what is the third number of n0, that's it. And you just define this sequence, phi n, and that's a subsequence, which not only is converging, but is constant. Well, I want to avoid this case, so I want to make sure that the range of xn consists of infinite number of points. Alright. It's going to make, let's say, the argumentation a little bit easy. Alright, so how am I going to do that? Okay, so let's take actually the range of xn. So I repeat, this is the set of points xn as when n belongs to n. And I'm going to call this set capital A. It's a set of points which is, I repeat, infinite. I want to make sure. Okay, so take the closure of A. It is definitively a set which is closed. Right? Since we have something quite clear here. A is included in K. K is compact, remember. So therefore K is closed. Remember, this is something that we say. So we have a set which is included in a closed set. Remember, this also means that the closure of A is included in K. Yet again, because K is closed. Why is that so? Because the closure of the set is the smallest closed set that contains the set A. So the closure of A is contains in K. All right. The closure of A is included in K. The closure, and it's a closed set, of course. But K is compact, so the closure of A is compact. All right. All right. So what does it mean here? So this is something that I want to keep for myself here now. Now I want to discuss two possible things inside this proof. There are two possibilities. Assume that there exists P belonging to the closure of A, such that for all epsilon positive, the ball centered at P and of radius epsilon intersect the range with a finite number of points. So in other words, I like to say it like this. For all epsilon positive, the ball centered at P and of radius epsilon intersected with A. It is a set of points, and it contains, of course, points in the sequence. And it makes sense to speak about the cardinality. I'm going to assume that this cardinality is infinite. Then in that case, I'm claiming that we will construct a sequence, a subsequence of xn, that is x and k, such that x and k converge to P. And in other words, we will be able to show that the set is sequentially compact. But I need to assume the other case, that is, this is not true. Alright, so assume this is not true. This means what? That for all P in the closure of A, I want to say that this is not true. There exists an epsilon positive such that the ball centered at epsilon at P and intersected with A consists only of a finite number of points. So you see, well, this is P, and you have only a finite number of points in the sequence, say 4. Well, guys, I mean, if such epsilon exists, I can make epsilon even smaller if I want, in such a way that there is 0 point, because P will be isolated, but it could be that P is a member of A. So I will say that the cardinality of this is either equal to 0 or 1, no more, but definitively finite. Well, I hope you understand that by checking those two cases, these are the two cases that could happen. Such a point P exists, or if such a point P does not exist, that it is that for any point you take in the closure of A, there always exists an epsilon such that the cardinality of the intersection with the ball and the range of the set itself is finite. And if it is finite, well, I mean, I can make it even small in such a way that there is 0 point in the case where P is not in A, and 1 point P instead in a case where P is in A. Now, you know, we don't know if P since the closure of A contains A, it could be that P is in A or P is not in A. That's the thing. All right. Well, let's talk about the first case. So I'm going to erase item number 2, but we will remember this. So I claim that if we are in the first case, we know how to construct a subsequence. How does it work? All right. So we have such a point P, and it tells me that for any epsilon you take, you always find infinite numbers. Well, infinite numbers, that mean some points which are different than P. All right. So take epsilon equal 1/n, and for each of those epsilon 1/n, take the ball centered of P and of radius 1 over n. Since I always have an infinite number of points, I can choose a point from the sequence. Let's say x. So I like to put not epsilon 1 over n, but epsilon 1 over k. It's more consistent. In such a way that x and k belongs to the set A. And also I can choose this guy in such a way that x n k plus 1, in such a way that nk plus 1 is always bigger than nk. Can I do this? Yes, because at each case, if I change epsilon from epsilon equal 1 over k to epsilon equal 1 over k plus 1, since I have infinite number, once I've chosen my x and k in the first case, it's chosen, okay, fine. Then I will be able to find a bigger number for the next step. So maybe I should go it step by step. So let's do it like this. We take this point P. Take the ball centered at P and of radius 1, simply 1. It tells me, I know that there is a member of the sequence in this guy. Okay, so let's take this guy. So I don't know which number is it. It says x and 1, which is in the ball. I take it. All right. Now, we want to take, actually, I take it back, you see, we want to take an epsilon a little bit smaller than this. So take epsilon smaller than the half of the distance of this. So you started with epsilon equal 1. Now take epsilon equal the distance of P and x in 1. Well, divided by 2 to make sure. Okay, so something like this. And it tells me, well, don't worry, we can find another member of this sequence in this ball surrounded by the red circle here. So it's here. So it could be that the index is less than, the corresponding index is less than n1. Well, take another. I mean, since there is an infinite number of those guys by assumption, take another which is bigger. Well, I'm going to take n2. And I'm going to reproduce the same thing here. Next step, you take epsilon equal the distance between P and x and 2. You still divide it by 2. Why not? Choose n3 bigger than n2, such that x n3 is inside the ball centered at epsilon of radius epsilon and centered at P. So you construct a sequence x and k, which converge obviously to P because the distance between x and k and P is less than the So I like to make sure that it converge, so let's say 2 to the power 2, makes the life easy. And at the step n, you take epsilon equal the distance of P with the former xn, okay? And you divide by 2 to the power k. Sorry, I mean, I have to change my mind all the time. You take epsilon equal 1 first, then epsilon equal the distance of the point P and the first point, you divide by 2. Then you take epsilon equal the distance of the point P itself with the next point you find by picking 1 in the range, and you divide by 4, then by 8, and so forth. So you're sure that the distance between P and this sequence tends to 0 as k tends to infinity. And this shows, of course, that the set is sequentially compact because I just have constructed a subsequence that converges to a point P. The point P could be in the sequence or outside the sequence. It doesn't matter, I don't care. P definitively is in K by respect because a case closed. Now let's look at the second case. The proof given in the book, I'm not so sure if it does not, let's say, have some bug. They speak about cluster point. I don't like really much this point. The problem I have is that the limit could be in the sequence or not. That's what I mean. So assume now that for all p belonging to the closure of A, there exists an epsilon positive such that the cardinality of the ball centered at P and of radius epsilon intersected with A consists only of let's say 1 point or 0. There's no so this is there's no point or there is one point. All right. And now I'm going to use the fact that the closure of A is compact. So this is valid for any point in the closure. So in particular, this is true for, okay, well, this is true for any point in the closure. So, okay, so for OP, so the epsilon, of course, depends upon the choice of P, of course. Huh? We have to make sure that if I take a point P and I take another point P, the choice of epsilon may be different. Okay, so for all P in the closure of A, consider the ball centered at epsilon P and centered at P. And you consider the union of this guy from P belonging to the closure. So let me rewrite this a bit better. Let's the union from P belonging to the closure of A of B epsilon P of P. Well, definitively, again, it's a little bit. It's pretty much the same thing as I did before to show that a compact set is closed. This definitively covers the closure of A. All right. But now, what does it mean? It's since the closure of A is compact, it tells me, well, don't worry. You just need to have a finite number of those balls. So that is only a finite number of those point Pi. So there exists P1, let's call it Pm, such that B epsilon P1 of P1 union B epsilon P2 of P2 union epsilon Pm of Pm covers the closure of A. Now, this is the thing here. Actually, you see, I claim also we don't necessarily need to say there's a 0 point or 1 point. Just a finite number, it's enough. Here, how many points do I have in the closure? Finite, a finite, a finite, a finite. So you have a finite union of finite points in the closure. But I assumed in the first place that I wanted to assume the closure of A to be of infinite, to have A of infinite cardinality. Well, if it has infinite cardinality, this contradicts. This is pretty much a contradiction that the cardinality of A was infinite. So actually, this case does not really happen. So this is the first case that happened, and we know now how to construct a subsequence, and that shows that finish the proof that a set which is compact is indeed sequentially compact. All right. So in what follows, we'll try to we'll do in the reverse situation. So the first thing I'm going to show next that a set which is sequentially compact will be totally bounded. We will see the definition, and from that I will construct this Lebesgue number and come back to the compactness. All right.